In the next section, we'll look at Hamming codes. We've seen just before that some things are not possible, so we can't always hope for an ideal code that gets all the errors corrected without spending extra bits. And Hamming codes will be some concrete examples where you can give a concrete recipe that corrects certain errors. And we'll see how close we can get these. But first off, we need a little bit of ingredients. And the first simple one is a parity bit. It's a simple idea that you may have seen before. It's maybe arguably the simplest possible error detecting code. It doesn't correct errors, but it detects errors. So you have some message here. It's just, how many are these? 9 bits? Who does 9 bits? Well, you have a message of a certain length, and you add 1 extra bit. And that extra bit is computed as the XOR of all the bits, or if you prefer, it's 1 if the number of ones is odd, and 0 if the number of ones is even. You could also say you add up all the digits and take that modulo 2, it's all the same thing. You may know that XOR is the same as addition modulo 2. So that's a very easy way to add an extra bit of information, 1 bit of redundancy. And if you now were to change one of the bits, if I were to flip this to 0, say, every single bit flip changes the parity of the number of ones, because it turns a 1 to a 0 or 0 to a 1. So if it was even before, it becomes odd and vice versa. So if I were to do that, I would also see that the parity bit flips. So by computing the parity afresh, so you take the first 9 bits and compute the parity, and if that doesn't match the parity bit, you know something has gone wrong. Another way to say what I've shown here is if I flip any single bit, I also have to flip the parity bit. That means the code distance of this code is 2. What are the code words of this code? The code words are all bit vectors that satisfy this equation down here in the general way where you put variables. So the code words are all the bit strings where if I add up all the bits, leaving out the last one, modulo 2, I get the last bit. That's not all bit strings, it's only half of them. And so whenever I take a code word and I change 1 bit, I leave the set of code words. But if I change another bit, namely the parity bit at the end, or one of the other ones, then I'm back into the set of code words. So there's some nice symmetry also going on here. So the code distance is 2. And from the lower bound section, that means we already can say what this means. If the code distance is 2, we can detect at most a d-1 bit error, so 1 bit error. And indeed, we can do this here. As you can check, flipping any bit changes the parity, and so you can detect if that happens. If the error is the parity bit itself, you would also detect that. And also, it's not strong enough to correct any error, because d-1/2 rounded down is 0. 2 minus 1 is 1, half of that is 1/2, rounded down is 0. So this code cannot possibly correct any error. It can only detect a single bit error. It's actually a bit conservative to say that. It detects more errors than just a single bit, but we can't guarantee that. It doesn't detect all 3-bit errors. Well, at least it does detect all 3-bit errors, doesn't it? What we can't guarantee is that it doesn't detect any change with at most 3 flips, because if you flip 2 bits, it wouldn't recognize the change. Okay, parity bits are used in many places because they make detection of these very simple bits, these very simple errors, flipping a single bit possible. And they're very, very cheap to check in hardware. So they're used in many buses and caches and unreliable memory. Usually in the scenario where you are able to correct the mistake through other means. especially these communication buses. If something goes wrong, they can just retransmit. I don't know how they did this with main memory. They detect an error in the main memory and then what? I'm not sure about that. So it's nice because it's simple and cheap. It's not very powerful. Brings me back to the question from before. Shall we do the game again? If I have 100 bits and I want to detect a single bit error, how many bits do I have to add? I think I'll leave that just open for you. Well, looks like there are some different guesses. The answer is 1. Okay, you need 1 extra bit, namely the parity bit. That's enough to detect one bit errors. I find this surprisingly good. Like it's a single extra bit. If you know the solution, it's kind of obvious. But if I did ask you before, how many bits do you think you need? And many said 5 or 100 or something like a substantial extra number. And for detecting a single bit, one extra bit is enough. It's kind of cool. Okay, but it's not very powerful. So if we want to correct errors, then we have to go further. And a typical application where this is real, it's a real concern. It's not something I made up. If you have a server that's supposed to run indefinitely, any downtime is really expensive. So even though some events are super rare, if you keep a server running for years, it's kind of happening. There's a nice blog post where someone did the math. Oh, you can't see. That's a good point. Now you can. Okay. A typical application for error correcting codes is this server that runs forever, supposedly. And there's a nice blog post where someone did the math and also tried to diagnose a mistake. So where you could pin down a crash to the fact that a program that he had on disk and in memory, as operating systems usually do that. If you start a program, they copy that into main memory so that it's faster to access. And there was a 1-bit distant difference between those two. So it's very likely that it was a cosmic ray that twisted a single bit in his main memory. These things happen. They're very rare, but if you run for a very long time, they do occur. And so instead of rebooting that server or crashing in some absurd way, it would be much better to have an error correcting code. And these things these exist, but they come at an expense. So let's see, if you think about this for the first time, what could you possibly do to correct errors? How should we possibly be able to do this? Because an error can be anywhere, so it seems like we have no big chance of correcting this. But the trick, of course, is what type of error are you able to tolerate? What type of error is likely? And if we ask for a single bit, then a simple solution is let's just store every bit 3 times. If you do that, then whenever you read a bit, you have actually 3 bits that you read, and you do a majority vote. Take the one that's more frequent. It's either 0 or 1. It will be one of those two. So if you ever only flip a single bit, it cannot compromise the majority of 3. And so you can correct this error. So it is in principle possible. It's a very simple construction. You can easily scale this up. If you wanted to tolerate more errors, you just add more duplicates of the same bit. But of course, like tripling the memory is probably not what you want. If building this error-tolerant main memory means you triple the cost of the server, you might get trouble financing this. But it turns out with a little more thought, you can achieve this scenario with 11% of overhead. So you need 11% extra bits or something like this scenario. Instead of the 200% overhead is if you triple it, right? That's where we're going. And this is what Hamming codes will eventually give us. How can we approach this? If we want to correct an error, it means flipping a bit back. That's easy to do if we know which bit to flip back. So it kind of reduces to locating the errors that happened. So how can we do that? The only thing we've learned in this lesson in terms of constructions is the parity bit. So it kind of probably has to do with that one. But interestingly, that's also enough. If you use several parity bits in a smart way, you can nail down where the error occurred. Now, you can't take several parity bits for the same whole set of bits. They would all be the same, so that's pointless. Instead, what you do is have parity bits for different subsets of the bits in the message. And then by taking the combination, which ones are corrupted, you can work out where an error occurred. So that's the rough idea. And the concrete construction can look like this. So there's the caveat that you can also flip the parity bits, but let's just look at a solution for this. We have a message of 7 bits. And I have 3 constraints. So this is similar to the parity bits. There was one constraint. I wanted that the sum of the first of the bits up to the last one is the same as the last one modulo 2. That was the parity constraint. In this case, we add 3 parity constraints, not just one. And so there's the blue subset of bits. The first 4 bits, they should be 0 if you add them up modulo 2. And similar for this green subset, which happens to take these 2 and these 2. And also for the magenta one. Why these 3 subsets? Maybe you can spot the pattern. It happens to be a good choice of subsets. Simple observation, if we don't observe, if there's no bits flipped, then by recomputing these 3 checking bits, taking the different positions and XORing them up, we can check that no error occurred. Then no error means all these checking bits are 0. Okay? What happens if some bit is twisted though? Let's say we flip this one. So there's a violation in all the constraints that involve this bit, because now I go from B3 to not B3. Wherever this occurs, I now get a violation, so this one will become 1. That's the checking bits I get if I flip B3. The beauty of this is I don't have to do concrete examples with 0s and 1s. It works the same for all bit patterns. And you may recognize that this happens to be 3 in binary, 0, 1, 1. And that's indeed a general pattern in with this construction. No matter which bit you flip, the checking bits will tell you in binary what position was flipped. And now maybe you see why these numbers work out well. We have 7 positions. I can encode 7 different things with 3 bits. But I can actually encode 8 different things with 3 bits. But I also have to leave 1 out for the case that nothing was flipped. Okay, that's kind of the general recipe. So this defines code words. I have bit strings that satisfy these 3 parity constraints. These are my code words. What I haven't told you yet is how to turn this into a code. So given your message, how can you compute these and how can you detect errors and these things? let's have a look at this. So that's the constraints we had. How do we turn this into a code? And what comes out of this is called the 4+3 Hamming code, or 7,4 Hamming code. I called it 4+3 because 4 bits are the message, and we add 3 redundancy bits. Notice that the colored bits here, they occur in exactly one constraint. This one only occurs the blue, this one only the green, this one only the magenta. So instead of computing the checking bits, what we can do is we fill the other 4 bits, the 7, 6, 5, and 3, and then we compute those colored bits from the parity constraints. There's a single choice for these bits that makes these constraints true. So more concretely, we put in the message bits. We can send 4 bits with this Hamming code. And then we XOR together different combinations of 3 of these bits. So for the blue one, we take the first 3. For the green one, we take these 2 and this one. And for the magenta, we take this, this, and this. Okay? So here it's spelled out with the indices. That way we compute the P's, which are called parity bits. And then you take this alignment of the bits and send that. That's the encoding step. I think it's a good idea to do a small example for that. I'll try to squeeze it both. Maybe I can zoom out instead. Try to squeeze it on one side. Oh, it's not too small. Who sends me a message? 4 bits. Doesn't matter too much. Anyone? What's your favorite 4-bit string? 4 ones. And so we take these and put them at these positions. So at position 7, 6, 5, and 3, 4, 2, 1 are left. And now I have to take the XOR of different sets of these, but because they're all 1, the XOR will always be 1. Shall we slightly modify the message? Maybe we make this 0 so that this becomes 0. Now the blue one is the XOR of the first 3, and that's 1, 0, and stays at 0. This one, the green one, is this and the first 2, otherwise known as leaving out the 5. That's 1, 1, and 1. That would give me a 1. And the last one leaves out the 6, this one, but that gives me 0. Right? I should probably have written these names. And then you can just follow the recipe up here. Ah, there's the ball. 3, 1, 0. Okay, I don't want to make a silly mistake, otherwise it won't work out. So these are the parity bits that we generate. And then that's the message that we sent. Okay. That's the encoding step. For decoding, we use the checking bits as before. So we receive this code, 7 bits, and we compute the checking bits, the ones from the first slide. And the checking bits will tell us in binary which position is twisted or none if it's 0. So let's do this on our example and say we flip one bit. Which one shall we flip? One of the parity bits maybe? We had this one before, I think. Let's flip this one. And we have to find the checking bits. Now, I don't think there's any way I can squeeze that on the same slide. But here's the formula for the checking bits. So the first one is taking the 4 leftmost. So we take, I could try to do this in the colors. If I take the XOR of all of these, I get 0. For the green one, we have to take the first 2 and then these 2. That's now a 1 because I flipped this bit. And the magenta one is every other bit. This one, this one. So here, every other on that row. And that looks like a 0. And if I read that in binary, I get that bit at position 2 is flipped, and that's the right one, right? The numbered 1 up to 7. Okay? And so if I know which bit was flipped, I can just revert the flip, and then I get the original message back. And this works no matter which bit is flipped. So as a procedure, again, you receive this, you compute the checking bits. If it's 0, you're good. Otherwise, you know which bit to flip again. And then you can return the message part by just stripping out the parity bits. Let's try to connect this with what you learned before about the lower bounds and this code distance. I think for that I have to maybe leave you a minute or two. Remember, the code distance is how many bits do you have to flip if you start at one code word before you can possibly get to another code word. Let's see if we can get this up to the 31 we had previously. Doesn't look like there's more answers coming. Anyone still busy thinking? Well, I'll leave it open, but show you the votes. So we got a peak for some numbers, 3, 4, 7, and of course the usual game. So the distance can't be more than 7 because any two 7-bit strings have distance at most 7. So that's an easy one. Not sure if any other conclusion is completely trivial. So what are the code words, first of all? I might have mentioned this, but the code words are all the 7-bit strings that fulfill the 3 parity constraints that we have. Now, if I flip one of the bits, we've just seen we can correct it. If I flip a second bit, we haven't really talked about what happens then. But if I flip 2 bits, there will always be a third parity constraint that fails. So if I flip just 2 bits, I will not get to a code word again, because it still can only satisfy 2 out of the 3 constraints at most. If I flip 3 bits, I might get into the region where I get into another code word. Because then I could, for example, flip a bit and the 2 parity constraints that that bit is involved in, and then I'm back. So yeah, the answer is 3. In case that wasn't clear now from what I said. You can find 2 code words that are 3 bits apart. And the fact that we can correct 1-bit errors shows that it also must be at least 3. Because if d is 3, that's for the first time where d minus 1 divided by 2 rounded down is no longer 0. Okay? Good. Let's have a brief look at what we achieved with this code, and evaluate this against the Hamming bound we've seen in the previous section. There are 2 to the 4 different messages, and each of these get translated into a 7-bit code word. So there's just these 16 different code words, really. Any of these code words, if I flip one of the 7 possible bits, I can convert it correctly back. I can correct that error and get the same code word back, and hence the same message back. So each of these code words is really covering 8 7-bit strings, which are all in its basin of attraction. And if I multiply this out, I have so many code words and so many bit strings that it attracts. I get exactly 2 to the 7, which means I'm covering the entire space of 7-bit strings. So it's not only that each code word has so many bit strings that are close to it. If I take all these balls that don't overlap, there's also the opposite property. Any 7-bit string is part of exactly one of these balls. So for the Hamming codes, they exactly partition the space of the code words, the blocks, into equally sized balls that all have one code word as their representative. So code distance is 3. We can correct 1-bit errors. Can we say anything intelligent about 2-bit errors? The thing is, what would happen in the code like I sketched it is we can definitely see that something's wrong. With 2-bit errors, we don't get another code word. But if you're 2 away from your code word, you're 1 away from another code word. And so you would correct towards this other code word. So the code would happily say, oh, that was a 1-bit error, and I know how to correct it. Here's the correct result, if actually 2 bits were flipped. There's a variant where you add an 8th bit so that this doesn't happen. Then you can detect 2-bit errors but not correct them. and you can still correct every 1-bit error. So both of these variants, the one I presented and the one with the 8th extra bit to also detect 2-bit errors, both are in wide use. Lastly, what I showed you is one instance of a general recipe. It's the smallest such code, if you want. In general, we can start with that number of bits. So we have a block size that's 1 less than the power of 2. Why that? Because then we can use these checking bits to address any position in there, plus the one that we need to say no error occurred. So we can use these L bits. We can use L bits as the checking bits to say which bit was flipped. And we can also conveniently use in the block all the positions that are a power of 2 as the parity bits. Maybe that's something in hindsight that is obvious here, but let me show this again. The parity bits here are at positions 4, 2, and 1. That's the powers of 2 less than 7. And these are convenient if you write the index of these in binary. You notice that whenever we had a 1, they participate in one of the parity constraints. So it's a very regular construction. And then the remaining n-L bits you can use for the message. If we choose a specific size L equals 7, then we get something that might be useful for main memory. We get a 64-bit memory. Well, we can cover the 64 bits in these n-L message bits, actually a bit more. And the overhead is just 11%. As you can see here, if you crank up L, n gets much bigger because here's a 2 to the L. So you add one more extra parity bit and you almost double the block, the message length. So arguably the Hamming codes are still fairly simple. They're definitely efficient to code, whether you do that in hardware or software. And they are much more space efficient than maybe one would have expected after this initial example of just tripling every bit. If you look at this more closely, you will notice that these choices for the message length as they come out of this recipe, they're somewhat special. These are the ones where this nicely works out, where the construction can exactly partition the space of 2 to the n around these code words. And people have called this a perfect code because it exactly matches the Hamming lower bound. And so we cannot possibly use fewer bits if we want to correct 1-bit errors in this scenario. The problem is that it is restricted to a certain subset of possible message lengths. These are not necessarily the most convenient. We like, in computer science, we like things as powers of 2, and powers of 2 are never among those, apart from the 4. So it's for these specific sizes of messages, the problem is solved, and the best possible solution if you want to correct 1-bit errors is the Hamming code. But in many other cases, it's quite open how to do this well. And there's an interesting result from the theory that says, in a sense, if you choose your code words just randomly throw them in the space, you have a large probability of finding a good code. But these codes are inefficient. There's no nice procedure like for the Hamming code, compute these parity bits and then you're good. That doesn't exist if you just use random code words. So in several ways, we know that it's possible to get good codes for other scenarios if you want to correct more bits or if you want other message lengths, but we don't know how to do it. There's only a theoretical result that they exist, but it's relatively useless as such because you can't really encode and decode these codes. And there's still some research going on into concrete constructions that try to push the frontier on these two things. That's all I want to say about error correcting codes. Just to tie this up with the compression unit, the two really go together, even though it seems like they're doing opposite things. Compression takes redundancy away, and here we add redundancy back in. But really what you want to do in communication is both. You first have data that might have redundancy built in, you compress it to remove that useless redundancy, and then you add controlled redundancy back in through error correcting codes to protect the compressed data from errors during the transmission. And the thing is that you don't add the same type of redundancy in. It feels like you're going just back and forth, but really the redundancy from compression is often not in the sense that it protects the data from manipulation. So you want to get the redundancy out in a way that can be inverted, and then sprinkle in redundancy in a convenient way tailored to the communication medium. And that's what the error correcting codes are about.